Alright, here's part 1 or part A of our Unit 1 review. And so we're just graphing. I'm going to go through most of these fairly quickly because there's just not much to it other than remembering what the graphs look like. Y equals -3. That's a horizontal line that goes through a y coordinate of -3. X equals 4 is a vertical line. X equals a number is a vertical line. That's going to go through an x coordinate of 4. As far as how I grade these, if I'm going to provide a grid like this, I'm not going to label the axes. Like I'm not going to mark that as a 1 and this is a 2. If you leave it unlabeled, I will assume that each block does represent 1 unit. If you decide to change the scale for any reason, then you must indicate that. So for example, if you decide each block needs to represent 2 units, then you have to label that to adjust for the change in scale. So let's see, it says horizontal line, vertical line. Let's go on. Number 3, that is also a line. This is in slope-intercept form, so my y-intercept is 2, my slope is 1/2, so I'm going to start at 2, slope is 1 over 2, so I'm going to go up 1 over 2, up 1 over 2, and I got to go to the left also, down 1 over 2, and then we'll connect that with the line about like that. There we go. 3 minus x, also in slope-intercept form. I did reposition it, so my slope is actually -1, and my y-intercept b is actually 3. So I'm going to start at 3, and a slope of -1 means down 1 over 1, down 1 over 1, and I could go up 1, left 1 as well. And again, I will connect those with a line, and we should have something that looks like that. So there's number 4. Moving on, y equals x squared. And this one you could get, if you forget what it looks like, you could plug points in. 0 squared is 0, 1 squared is 1, 2 squared is 4, some of it y equals 4, 3 squared is 9, which is way off the graph, so I won't worry about that. And then it will reflect back this way. And so we'll connect it like that. Oh, geez, that was bad. Let's try that again. Oh, no, no, no! Undo. There we go. It's hard for me to connect it with this. There we go. That's a little better. So make sure when you're doing this, just in case you do have a hard time connecting the dots, make sure that you make the points you're trying to hit nice and bold so I can see what you're trying to do. That way if you miss it, I can still see what you meant to do. X cubed, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, which is, I'm maxing out at 5, so 2 cubed is going to be like somewhere way up there. -1 cubed is -1, -2 cubed is way down here off the graph. So when you're connecting that, you do need to be aware that at 2 and -2, you should be at 8 and -8 values. So don't come in and do something like this. Don't plot those 3 points and then do this, because what I've drawn right there, I've shown that at 2, I'm at a y coordinate of a little over 3, and 2 cubed is not a little over 3, it's 8. So when you're connecting these, make sure, I'm just going to do all that, make sure that you are staying inside that 2, because we're not supposed to be at 2 yet, and then it does this little s thing through the origin, and then it goes back up. So there's x cubed. Getting a little bit more difficult. Absolute x is not too bad. That's your v with a slope of 1 on the right side of the origin and -1 on the left side. There we go. Sine x. And this is one where I'm going to have to change the scale on the axes. I do know that the max of sine is 1 and the minimum is -1, and I may even change my y also to give me a little bit more breathing room. So I'm going to call that 1. I'm going to call this -1. And then sine x starts at the origin, then it has a maximum, an x-intercept, a minimum, x-intercept, maximum, and it does continue both left and right. So I'll do that. And then when I connect it, it's going to come in something like this. Oh, geez, this is going to be bad. I'm going to try to connect. Actually, I'm just going to do this real quick. There we go. Kind of ugly, but you can see what I did. Now, on this one, if I don't relabel the x-axis, I'm going to assume that this is x equals 1, this is x equals 2, this is 3, and this is 4. That is not what the x-axis should be, because the period of sine x is 2 pi. So you need to indicate that change in scale somewhere. We could just do a simple mark this spot as 2 pi. If you want to kill it dead, we could mark this spot as 1 pi, This spot would be pi over 2. You don't have to label every single one, just enough to establish that the scale for each unit is not 1, but each block actually represents a pi over 2 for the period of sine x. See, cosine is going to be kind of the same way. I'm going to relabel the axes. I'm going to go up to 1 here and down to -1 here. And cosine starts up at the origin, up at y equals 1. Plot your points, and then we'll come back and draw the waves. There it is. And then again, just like with sine x, you need to establish that the period ends at, the first period ends at 2 pi to reestablish the scale for the x-axis. Tangent x, again, we're going to have to reestablish the scale on the x-axis. I am interested in the asymptotes here and here, and actually the way I've done that, my next asymptote would actually be over here off the grid a little bit. And your asymptotes for tangent x, they occur at pi over 2 and x equals -pi over 2. And then comes up, hits the origin right there. Follow, oh geez, that was bad. Follow that asymptote, go through the origin. Has kind of an x cubed type shape, except x cubed does not have vertical asymptotes. This one will do the same thing here. It's going to cross over that x coordinate. And the x-intercepts are your multiples of pi. So that's like 0, this is 1 pi. 2 pi would be over here in this case, the way I've drawn it. So asymptotes at -pi over 2 and pi over 2, and then your x cubed type shape. 11 and 12, change 11 to secant x. I did not mean to repeat that. And 12 is cosecant. And for both of these, I'm going to start by remembering that secant x is 1 over cosine. Cosecant x is 1 over sine. And in graphing these, I'm going to start by graphing cosine x and sine x on both of them. So I'm going to do that real quick. There they are. And so I graphed those, and again, I had to establish or show that I've changed the scale on my axes. I forgot to change my y-axis, so I need to do that. So indicate any change in scale that you have. And for both of these, the graphing is very similar. You're going to start by dropping vertical asymptotes anywhere the sine and the cosine hit the x-axis. So I'll have a vertical asymptote here, vertical asymptote here, all of these places where sine and cosine intersect the x-axis. Those are vertical asymptotes for secant and cosecant. There are the vertical asymptotes. And then finally we will come through and we will graph secant and cosecant by putting the little u's on the humps and between the asymptotes of sine and cosine. And this green graph is the actual graph of secant. The blue graph for cosine, that's just a visual to help me get secant done correctly. You don't have to erase the cosine graph, you can leave it there, I'll understand what you're doing. And then we'll do the same thing for sine x. There we go. Alright, so there is secant and cosecant. Those are probably going to be the most involved ones of all the functions I want you to graph. 10 to the x is not too bad, so you can just plug in values. Anything to the 0 power is 1. 10 to the first power is 10, which is way up here. And then there is a horizontal asymptote on the x-axis. So the line y equals 0 is a horizontal asymptote. And then I will come up this way, starts following that, and then it takes off in a hurry going up towards 110. So it's going to look something like that. E to the x is also exponential, so it will also have a horizontal asymptote on the x-axis. E to the 0 is 1, just like 10 to the 0 is 1. But when I plug in 1 for x, e to the first power is going to be e, which is about 2.7. So I'm going to go through the point 1e, following the same general trend as 10 to the x. There we go. 2 to the x, same as 10 to the x and e to the x, has a horizontal asymptote on the x-axis. It's another exponential function. 2 to the 0 is 1. 2 to the first is 2. This one, though, I can plug in a few more points that will fit. 2 squared is 4. 2 cubed is 8. And so that's going to be here. And so I do want you to hit the whole number or the integer coordinates where you can on these exponentials. 10 to the x is hard to do because when x is 2, 10 squared is 100. And we're not going to have a y-axis going all the way up to 100. e to the x, because e is an irrational number, yeah, 2 might fit, e squared might fit on here, but I don't know what e squared is, so I'm not going to worry about that because it's some irrational weird number. Log of x, again, vertical asymptote. Oh, that's a thin vertical asymptote. This will have a vertical asymptote on the y-axis, and all logarithmic graphs, the 2 key points I'm going to look for are they have an x-intercept at the point 1, 0, or at x equals 1, and then they will also hit the point, whatever the base is, 1. Log without a base written, it's known as a base of 10, so it's going to hit the point 10, 1. We'll follow the vertical asymptote, we'll go through 1, 0, then we'll have to scoot on over to hit 10, 1. Natural log x is log base e, so again, we'll have that vertical asymptote. It's a logarithmic graph, so we'll have the vertical asymptote on the y-axis. It will have an x-intercept at 1, 0, and it will hit the point, so it hits the 1, 0, it will hit the point base. The base of a natural log is e, 1, so e is about 2.7, 1, and that's the point I'm going to look for. Oh, missed it. Let's try that again. Yeah, that's a little better. Kind of ugly, but whatever. Log base 2 of x, again, vertical asymptote, y-axis. I want you to hit the point 1, 0 and the point 2, 1. Now this one technically does hit the point 4, 1 also, but I'm going to be consistent with this one as I was with the rest. The key points I'm looking for are 1, 0 and whatever the base is, 1. So as long as you're coming up and hitting 1, 0, well, and 2, 1, I'm okay. This is really ugly. So I'm going to come up 1, 0, 2, 1. That's good enough. If you want to be awesome and hit 4, 2 as well, you can. Alright, 19, y equals 1 over x. There's only 2 integer points I'm interested in you hitting. Now this does have a vertical asymptote on the y-axis and a horizontal on the x-axis. If I plug in 1 for x, 1 divided by 1 is 1, so we need to hit the point 1, 1. If I plug in negative 1 for x, 1 over negative 1 is negative 1, so I have to hit the point negative 1, negative 1. And then it follows the asymptotes and goes down this way. I'll be looking for you to hit that point 1, 1 and negative 1, negative 1. And then I also want you to follow those asymptotes. You don't necessarily have to draw the asymptotes in there, you just have to be aware of them. So if you don't want to put the dotted lines, that's fine. Just make sure that you're not crossing any of these asymptotes that we have here. 1 over x squared, same thing. We will have vertical asymptote on the y-axis, horizontal on the x. And if I plug in 1 for x, 1 over 1 squared is still going to be 1. Negative 1 squared, though, if I plug in negative 1 for x, that becomes positive 1. So when I plug in negative 1, it ends up being 1 over 1, which is, again, 1. So 1 over x squared, both sides are actually above the x-axis, still following those asymptotes. Yep, there we go. And then finally, the last of the graphs is the square root of 9 minus x squared. This is in the same form as the square root of r squared minus x squared, which was a semicircle with a radius of r. Actually, that would be negative r over there, I guess, r. And it would go something like this. So here, it is a semicircle shape, but in this case, my r value is going to be the square root of 9, which is 3. So we'll have a semicircle that is extending out to 3 in all directions. And this is only the top half of the circle. So there are all of the graphs 1 through 21. And you need to be able to recognize them and go backwards also, because I will give you some of the graphs and you have to write the equation of the graph. Sometimes I'll give you the equation and you have to graph it.